All right, here's part 2 of 2.1, the worksheet where we talked about oxidation states. This part is where we're looking for items that are changing their state between when they are a reactant or when they are a product. Okay, and there's a couple things that you need to keep in mind with this. We're looking for things that are either oxidized or reduced, and we use an acronym that goes LEO, says GER to help us out. Okay, and LEO stands for lose electrons, oxidized, and GER stands for gain electrons, reduced. Okay, so we're looking for a change where we have different charges from the right side to the left side. So the first thing we need to do is we need to assign oxidation states to each one of our elements inside of them. And so we're looking for the charge of one atom of each. What's up? Stuff. Okay, cool. Put it on the back counter in the back room, yeah. Is there a room in there in the hood? Okay. Do we have enough stuff to do this lab next year too?
Yeah.
Okay.
Yeah.
Okay. Like, how many, like a couple years or like?
Probably a couple of years.
Okay.
As long as the sodium hydroxide doesn't get used up.
Okay.
The only thing that might run out is the ammonia.
Okay.
That's the only thing, but we've got 2 jugs of that.
Okay.
It just depends on how much you'll use.
Yeah, I have no idea how much I'm gonna get to this year, so we'll see.
It's just 'cause you have to use it basically straight out of the bottle for the 15 molar stuff.
Gotcha.
So if you use a lot of it, then that's gonna.
Bye-bye.
Yeah.
Go away. All right, cool.
The only thing that I don't have in here is the aluminum reagent.
Okay.
I don't know.
Yeah. Yeah, don't worry about that one quite yet. I'm not sure when I'm going to finish this lab because they finished the unit that this lab is in, and we haven't finished the lab. So, yeah. That's a part of the trick of being able to do more labs is getting them all in the time span that I want. So, we are going to finish this one though.
The 50 milliliters ammonia is nasty.
Yeah, that's intense.
I opened up the bottle and poured it in there, and it was like.
Yeah. Okay, well, cool. Thank you.
Oh, did you get the purchase order?
Yes, I still owe you the Amazon list too, because there was nothing on that I gave you that was Amazon.
Yeah, at least not that I saw. I might see.
No, I made a separate list with Amazon because I had actually emailed it to Ray already. Because last year he just let us just send it to him, and we didn't have to put it in the PO. And this year we have to put it in the PO. So I will send that to you, and then we can get that done. All right, thanks. Okay, so zinc because it's a solid has an oxidation number of 0. Oxygen is -2. All right, but what we also have to keep in mind is that we have this negative value here. So I'm going to put this around here and move the negative out here for a minute so I can see what's going on inside. All right, so what this negative means is that between the charges of the nitrogen and the charges of all the oxygens combined, I must have an overall charge for this molecule of negative. So I'm going to put a -2 on top of oxygen because that's our standard charge for it, times 3. This will be -6. And now I want to keep one of these negative charges, so this nitrogen here is going to be +5. +5, -2. Okay, hydrogen is positive 1. Zinc on the product side is positive 2. Oxygen is minus 2, and I've got 2 of those, so the overall charge will be minus 4. Because this overall charge here is minus 4, all right, that means that this nitrogen is going to be plus 4. Oh, plus 4 minus 2. And then over here I've got hydrogen, which is plus 1, and oxygen, which is minus 2. This will balance each other out because I have 2 hydrogens making the entire hydrogen side plus 2. In this process, we really don't have to worry about the stoichiometry with the coefficients because that's just saying how many of these molecules we have all together. It doesn't affect the charge or the oxidation state. Okay, next thing what we're doing is we're looking for changes. So I've got an obvious change here. This goes from 0 to plus 2. And then the other change I have is nitrogen going from positive 5 to positive 4. Okay? So let's look at this. We're looking for the first one, which is the Leo. How do we lose, where are we losing electrons? Well, remember when we lose electrons, the charge actually goes up, okay? Just for example, if I had something like carbon, carbon has 6 protons, 1, 2, 3, 4, 5, 6, and 6 electrons. So if I were to take away one of these electrons, now it becomes positively charged. Take away 2, it's now positive 2. Take away 3, it's positive 3. Likewise, if I add those 3 back on, now we're neutral. Add another one, or negative 1, negative 2, negative 3. Okay? So charge is a combination of our protons and our electrons, and which one outnumbers the other. Okay? So here I have 0, and now I have lost 2 electrons to gain a positive 2 charge. So this is our oxidation, okay, or our lose. And then over here, and I'm going to put a little E on here, so we actually lose 2 electrons. And then over here, I've got another one where I've gained 1 electron. Okay, and that's my redox, okay, or reduction. Okay, reduction, oxidation. Let's take a look at another one. Okay, I'm going to skip down to this one again. Okay, calcium starts with 0. Oxygen and water minus 2. Hydrogen plus 1. I've got 2 of them. Overall charge for both combined is positive 2. And I have H2, which this is 0. Hydrogen is plus 1. This is minus 2. That gives me a negative 1, okay, for our overall OH. And because there's 2 of them, minus 2 for the 2 OHs, or hydroxides, giving me an oxidation state for calcium of plus 2. Okay, and I think we can go from there. So calcium has 0 charge, and it's going to end up being a positive 2. All right, remember when we lose electrons, we gain positive charge. So we lost 2 electrons, so this is our oxidation. All right, and we're also looking for this hydrogen here. And this hydrogen here is going to get a little creative with my boxing. It is going to go from a positive 1 to a 0. Okay, so it is going to gain 1 electron. There's our reduction. So when we talk about reduction, we're really talking about a reduction of charge. Now, one thing I want to point out with this one is notice that hydrogen does not reduce 100% of the time. We still have some hydrogen in here in calcium hydroxide, which is going to stay at the positive 1 charge. So just because there is a reduction doesn't mean that we're going to have all of that elements or species being reduced. Okay. Let's see here. Let's try one more. I'm going to try, look at 57A. All right. And here's the thing is when we have things that don't have a lot of hydrogens or oxygens, we want to go with the most standard charge for an element. Okay, so like this CdCl2, you're probably going to want to look at your periodic table. Chlorine, while you don't have to memorize the common charges of these, is really helpful to get used to knowing what they are. Chlorine is sitting over here just below fluorine, okay, and it's one of the halogens, and we see that its charge is -1 for all of these. So we're going to kind of want to commit these a little bit to memory. It just makes life so much quicker. Same thing with the charges for the knowing kind of who's in the alkali and the alkaline earth metals over here. Okay, these are these are +1s and are +2s. All right, so I have chlorine over here. Chlorine is a -1. I have 2 of them. Okay, so that means my cadmium, the CD, needs to be +2. Okay. Sulfur's most common charge, sulfide, is -2. Sodium, I have 2 of them, so I'm going to split the +1 twice. Okay, so this is going to be +2 between the two. If you want to put the total charge of those over there. So I'm writing the oxidation states along the bottom. Okay. Now we have CDS, and CD is +2 over here, and it works out perfectly that S stays at -2. Over here we've got NaCl, and Na is typically +1 and chlorine is -1. So in this case, I'm going to put those down here for consistency. In this case, we have chlorine, which is -1 as a reactant and -1 as a product. CD +2 product reactant, and then reactant for product for Na. So there's no redox here, okay, and that's perfectly okay. We don't have to have that, but in this case we don't have a transfer of electrons from one element to another. We just have a switching of compounds. So this is actually a double replacement in our traditional terms. Okay, so there's some overview and some help on some of those. Here we go.